Dr. Lichtl is a founder and CEO at DeltaBrain Inc. DeltaBrain Inc. is a Pasadena-based AI startup focused on bringing reliable pattern recognition to continuous healthcare monitoring data. DeltaBrain's software enables doctors and nurses to make better decisions more quickly. Adam's career has spanned a variety of things. He has a undergrad right here from Caltech and a PhD in fundamental physics. He's worked in finance. He's also worked at SpaceX. He was director of research at SpaceX, and that's actually where I got acquainted with Dr. Lichtl. He was my boss when I was an intern at SpaceX. So you can ask him about life there as well. Nowadays, he's moved on. Instead of launching humans into space, he's helping humans here on Earth with his new startup, which is here in Pasadena. And he's going to tell us about all of these things in 30 minutes and leave 15 minutes for questions from the audience. Does that sound good? Okay, I will lower the lights a little. Are you going to show the video first?
Yeah.
Okay.
Yeah. So what I'd like to talk about today is kind of the art of software and the processes around software, not so much the nuts and bolts of writing software, because you're already learning that and it's already something that gets a lot of focus. I'd like to talk a little bit about the other halves of things. So what I'm showing you here actually is a simulation we did at SpaceX, and Christine was actually a critical part of this project, where we are trying to simulate the mixing of the propellants in the rocket engine. The reason that's important, aside from being just gorgeous, the reason this is important is because you want to optimize your engine design. The more efficient your rocket engine is, the more likely it is you'll be able to get to space. And it's a funny problem because you can't really get to space on a clunker. If you imagine I have a rocket engine that's so efficient, you think, well, I'll just put more of them on the rocket. So I might have a lousy engine, but I'll put 20 of them on the rocket. And people actually tried this back in the 50s and 60s. The problem with that is every engine you put on adds weight. And so you need more thrust to get to space. So you need to put another engine on, but that adds weight. So you need more and more thrust, and more weight gets added, and you never actually close that loop. And that's actually a very important concept in rocketry, is the idea of closing. The engineering case has to close. And by that, I mean you are generating enough thrust to lift yourself by your bootstraps up into space. And so efficiency really is everything, because for the same amount of weight, you need the most thrust possible. And that's pretty much the definition of efficiency. The efficiency is driven by how quickly your propellants mix. Don't worry, it's not all going to be a propulsion lecture. But I always thought this was an interesting thing, is that you have you can imagine a big 42-gallon drum, like you see oil come in. That's about how much propellant one engine at SpaceX burns in a second. So 300 pounds a second goes right through the engine, out the back, gone. And so in the time it takes for the liquid oxygen and the kerosene to come into this little tiny tub, right, which is the engine, and then get shot out the back 300 pounds a second, you need to actually mix them and burn them and release all that chemical energy and channel it into thrust by using the nozzle. That's not a lot of time to do all those chemical processes. And the mixing is really the thing that drives your efficiency. So if you ever see a car going down the street and black smoke is pouring out of the back, and every once in a while you hear it backfire out of the muffler, what you're actually seeing is uncombusted gasoline. So in this case, there's the liquid oxygen. It's just the air from the atmosphere, because you don't have to take your air with you here on Earth. And you've got liquid gasoline in your tank, and it's trying to be burned in your engine. It has actually, compared to the rocket, it's almost an infinite amount of time to burn it, which is why pistons and things, you can get away with all sorts of sloppy mixing in a car. But if you're really bad, then some of your gasoline will go in, it won't burn, and then as it's heated up, though, instead of burning, it just kind of makes these knotted hydrocarbon balls. And the color of those is black. And so when you see soot coming out of the back of your car, that's actually wadded up, unburned gasoline. And so that's the idea of when something's burning dirty, it's also burning inefficiently. And so that also is a consequence of poor mixing. So back in the day, if you wanted to send a rocket, say, to the moon, you really just had to do one simple thing. Well, you had to do two things. One is you had to go hire a team of probably the smartest engineers in the country. Great, check. And then you had to go get a blank check from the government. And so that's what they did during the space race. They basically got an unlimited amount of money from the United States government to put a man or person on the moon by the end of the decade, back in the 60s. And they spent that money quite well. So, they were blowing up engines all the time. They had 3 independent test sites that they were actually testing different variations of the engine. And by taking an evolutionary approach, they were doing trial and error, and they were literally blowing these things up. There was actually one flaw in the F1 engine that they spent a year working the kinks out of. A year. 1,000 tests. Basically a test every single day at each of 3 sites for a year. And they figured it out, and they figured it out by trial and error. In the modern era of space flight, you have private companies, such as SpaceX and others, that are trying to innovate on top of this. So they're not starting from scratch. They have this base of knowledge that was developed. But they want to innovate on top of that and make efficient engines and carry heavier payloads to orbit and do extra things, like bring the rocket back. Now, if you want to bring the rocket back, you don't put a parachute on it. And so I'll do a little tiny digression here. Is, the reason why you can't just throw a parachute when you're trying to bring a rocket back from space is the same reason people die when they jump off a bridge into water. And so as a kid, I never understood that. I'm like, it's water. I go off the diving board all the time. How do people, kill themselves by jumping off of bridges? Well, it's because the speed at which you're going versus the change in the density basically gives you your force. So if you're coming off of something in air and you're going very, very quickly, suddenly your body is moving through a much denser medium, water, and that deceleration is what crunch like a can. Now, the same is true in space. Space is extremely low density. So compared to that, just the atmosphere is like water. It's that much denser than, not quite vacuum, but pretty close to it. So when you're very, very high up and you come back down, and we've seen people jump out of those balloons like Baumgartner and those guys, the Red Bull team, they're not going that fast. So they're going in, and it's gradually becoming denser and denser and denser, and they're slowing down, and it's fine, and you can throw a parachute. But if you're a giant chunk of metal weighing several tons, and you're coming down at, I think it was 7 times the speed of sound, and you go into the atmosphere, well, crunch, like a tin can. So what you need to do is right before you go crunch, you fire your engines one more time. But instead of pushing you forward, you're actually firing them down to slow yourself down. Not to stop yourself. You're not hovering at the top of the atmosphere. You're not even really doing a controlled descent. You're basically going, ah, and then you're kind of pushing on the gas. You slow down enough so that you come into the atmosphere, and it still hurts like heck, and you have to design the rocket for that, but you don't crunch like a tin can. So what that means, at the end of the day, from an engineering standpoint, is your engines actually have to be so efficient that not only can you lift yourself and all your junk and underwear for the astronauts to space, you actually need to be able to slow yourself down by firing your engines a second time when coming into the atmosphere. And then, of course, you probably want to fire your engines a third time before you hit concrete. And so that's why it's so important, even now, to optimize the mixing of propellants inside of a rocket engine. So our team at SpaceX was in charge of building this simulation. And what you're looking at here is the mixing of basically the propellants going into the engine, and that will inform the efficiency of the combustion process. So that's a fun preamble. Can we get the lights back up? Yeah, sure. I always fall asleep in the morning, so I don't want you guys to see me fall asleep during this lecture. I think that would be rude of me.
There we go.
So does anyone have any questions before I kind of go on? I know we have questions at the end too, but feel free, if there's anything about this before I move on.
And are you done with the screen?
I'm totally done.
Okay.
Yeah, thanks. Yeah. OK, so the point I want to make, actually, that's kind of the story of why to do something. But today I'm here to talk about how we actually did it. And I'm in healthcare now, so I'll get to that as well. But I think what's important about this simulation is this is not the work of one person, or 3 people, or 5 people, or 8 people. This is the work of, about 10 people over the course of several years, 4 years to be exact. Even by that standard, it's an incredible amount of work. You hear about projects where giant companies like, and I won't name any, but giant companies will come in and they'll spend years with a team of 100 software engineers, and they'll build garbage. It won't work. People will use it, they'll hate it, doesn't get the job done, it crashes. So what is it that made our team special? Were they extremely talented? Yeah, sure, but so are the teams at these big companies. Was there a lot of urgency there? Yeah, but urgency usually leads to sloppiness. So what's the secret sauce? The secret sauce, in my opinion, and I think this is very relevant to people who are starting out as software engineers, who are maybe someday going to go into that field, or maybe have been in it all along, or maybe just will have this as a component of your job in the future. And I feel like nowadays, no matter what you do, almost, whether it's anything from art to even theater, actually I have a theater friend who uses some software engineering, to obviously the hard sciences, you will always have a component of software engineering. So what's the difference between good software engineering that lasts and gets the job done, and shoestring code that gets rewritten every time a new team comes in? The difference is process. So the process of software engineering is a very important thing. And you actually can go back to the period of the Renaissance when you had all these artists. And you said some of the best art in the world was made during the Renaissance. And you say, wow, it's just how lucky. You just had all these great people who were alive at exactly the right time, and they all made a bunch of amazing art. And then it kind of went away. It might be back, but you know. What's interesting about the Renaissance is all of that art was actually, most of that art was sponsored. So you actually had very wealthy either individuals or the church, or you had large organizations, even cities, would commission works of art. The Sistine Chapel was painting a ceiling, right? The doors of the baptistry was building doors, right? So this is, you know, Florence and Rome and all these different places. But all around the world, you saw people commissioning family portraits. And what all of those things had in common that you usually don't have in art is a lot of structure. I want you to paint the Sistine Chapel. Okay, great. I'll start tomorrow. Well, wait. The roof is measured like this. There are curves like this. I need it done, you know, over this period of time. It has to have exactly this content, and it needs to have this feel. We like this part of your art before, but not that. So you have this interesting dynamic where art and creativity, and I do believe software is ultimately a creative act. And that's because the definition for me of creativity is how much decision, how many choices you have to make in doing something. When I change a tire, I know exactly the sequence of steps and how to do them. There's no creativity there because I have no choice in what I do at each step. With software engineering, it's the exact opposite. Literally not every moment, but pretty much 50, 60 times a day as we're writing software, we have to make decisions because there are more than one way to do things. And the same is true in art, even how you express a concept. And when you think of that as expressing a concept in a medium by making personal decisions on how you do so, you see that art and software engineering aren't so different. So in the Renaissance, it's kind of interesting because they had all this structure. And you talk to any artist, or any software engineer for that matter, and they'll say, well, don't tell me how to do my job. I'm the artist. I'll show you how to do it. But the problem with that is you end up with too broad of a scope, and it can get messy quickly. Whereas if there's structure, you're not telling Michelangelo what paintbrush to use. You're not telling him his color palette. But at the same time, you are stripping away a lot of the random choices that he would have to make in that situation. He knows exactly the problem he's trying to solve. He knows exactly the constraints on that problem, and then he is free within that structure to be as creative as he wants. So that's how they're similar, art and software engineering. But one of the ways they're different, and it's a key way, is the fact that it's a team effort when you're writing software. So that's really the second big aspect of the process, is that you actually want to have a structure in place where you're not just letting people individually be creative within some set of well-defined constraints to accomplish something. You actually want to have groups of people not stomping on each other and working well together. And it's interesting because if you look at skyscrapers, if you look at any large endeavor done by humankind, including rocketry, you actually see it's always a team effort, right? And it's never a kind of divide and conquer. Nobody said, okay, here are the engines, go build those. Okay, here's the life support system, go over there. Here's the fuel tank, go over there. And in 6 months, we're all going to come back in this room, and we're going to bolt it all together, and we're going to go to the moon. That's absolutely not how rocketry works, and it's absolutely not how software works. There are so many interactions among the different pieces that you actually have to be really careful about how you connect all those together. So I just want to make the point that as you learn software, either professionally or just for fun, always keep in mind that what you're learning is how to chisel stone. You're learning how to make a sculpture. But what you're not learning is how to actually make skyscrapers and cathedrals and all these wonderful things, because to do so, you actually need more than one person. And so always keep in mind, and it's funny because I'm one of those people that I really like writing software and I really like creating, and I really have kind of an ego around that where I'm like, okay, I'm going to go in my hole, I'm going to make something amazing, come back. And I've had to basically fight that for 15 years. And basically, I've finally mastered it, and I was able to make something like this, because that wasn't me as the only person programming. I learned how to first work well within a team, and then help lead those teams. So yeah, I think I'll pause there for a second. Are there any questions on any of that? It's one of those like soft lessons, right? You're like, okay, I'm going to talk about AI and all that stuff, which I'll talk about next. But I really want, if you take away one thing from this, it's actually the process of software engineering that makes someone good. So when we interview at Delta Brain, I basically test for two things: raw intelligence and the ability to adapt to a changing situation based on feedback from another person. So we actually, that's it. And in terms of resumes, we look at, like, do you know 2 programming languages? Because if you know 2, that means you didn't just learn one as a one-off thing. You actually care about software. And so if you translate that to art, it's like, can you swing a hammer into a chisel holding it on a piece of rock? Yes? Great. OK, you're not hired yet. Now, can you work with these 20 other stonesmiths and build an arch that doesn't fall down? OK, if so, then welcome to the team. So
you said you learned how to work in your data. So what did you change in your coding to be able to work with other people?
that's a great question. So I'll repeat the question. That's a fantastic
just repeat the question, thanks.
Yes, absolutely. So the question was, I mentioned that I had to change the way I approach software engineering to become effective at it. And by doing so, becoming more effective in teams of other people. The question was, what did I actually change? What was different? It's a fantastic question, because that's really the guts of what I'm trying to say is there are processes in place. So one example is unit testing. So, unit testing, like in that class I took. Unit testing is critical. It is the cornerstone. And the reason why is because if I go into, let's say you start a new job at a software company next year. And that software company could be NASA, right? That software company could be Google. That software company could be something you make yourself for, medicine. Whatever it is, you have a component of software. And you join this company, and you have a code base that exists. And so you want to improve it, right? As you're a creative person, you have new functionality you want to make. So you sit down, and you have 2 problems facing you. One is the obvious one, which is whatever you touch, you might break. So that kind of leads to the, I'm going to go over here and make my own version and then give it to someone who has more experience with that code base and see if they can connect it together. That's a nightmare and a mess, and it also irritates people. But you have an even bigger problem before that, which is, does the thing you think you're going to contribute, does it already exist somewhere in the code base, buried? Like, are you rewriting some special thing that actually already exists, you just didn't know about it? So what's the best way to learn about what's in a software code base? People say, oh, well, read the documentation. And I say no. I actually think documentation is absolutely worthless, so I'm undermining all the education of all the software engineers. Totally worthless. Worthless. We don't write any documentation, which is not true, actually. We have a lot of DevOps documentation. What is essential are unit tests. Because for me, the unit tests are the documentation. I am looking at a small bit of code that is telling me exactly what I'm trying to accomplish in each unit of functionality. I know the interface into the code base to run that, because that's what the test is. The test is, can I create a user? OK, now I know the code base can create a user. I haven't even read one line of code. I just looked at the name of the unit test. Then I go in, and I go, users.create, blah, blah. Oh, there's a users object. Cool. Oh, and it has a function called create. Well, what does it take? Oh, it takes a social security number. Oh, I didn't know that. We need that. OK, so maybe when I write something, I can do, for people who don't have a social security number, I can add to that. Well, wait, let me check if there's a unit test. Oh, there is. 3 lines down, there's a test, create user without social. Oh, OK. That is how I learn every code base I ever work with. And that is how I allow people who are new to the code base that we build to learn it. First week anyone spends at Delta Brain is going through the unit test. Just go through the unit test. First of all, if you can download, compile, and run the unit tests, you've already basically built the code base and ran it. That's already a ton of work. That means all of your tooling is set up, all of your ability to execute the infrastructure around it. If it's a cloud system, you need to have special instances. It means you can connect to the databases. All of this stuff that you would typically do as some hideous checklist that's painful, you have to do just by virtue of running the unit tests. So that's one facet that I think is very different in how you have to change when collaborating with people, is that when you communicate with a person, people like to go to a whiteboard and scribble, this is my algorithm, this is what I think it should do. Or they like to hand them a chunk of code and go, here's a prototype, run it off to the side. But in a really collaborative environment, you actually have a quick discussion with someone about the functionality. Just make sure that maybe in their head they have something that isn't captured in the unit test. But then go right in and write a piece of code that is in the system with unit tests, and then submit it. And people will review that, and they'll see, wow, this actually works, and then they can merge it with the code base. So the second big piece of collaboration in software engineering is good hygiene around checking in your bits of code. And I don't want to get super granular here, but we do continuous integration, which again is critical. And to me, it's important that when you hear me say critical, you don't think I'm just like a cheerleader for everything in software. Because like I said, I hate documentation. So I don't agree with everything that's out there, but I swear by test-driven development and continuous integration. Those two practices, more than anything else, will basically, if you're interested in money in software engineering, they'll add a 0 to your salary at the end, the right end. Because doing that makes you very effective in a team. Yes?
There's that many people you're having to work with. To what extent do you have to worry about leaking?
As in information?
As in proprietary methods?
Sure, that's a great question. So I'd like to I'll repeat that question. I'll actually expand it a little bit and answer that. The question was, when you have a team of a lot of people, do you now have to worry, or if you are worried, how do you deal with people leaking information out, whether it's copying the code base and distributing it or explaining algorithms to other people? It's a really interesting time in history because the algorithms are really distinct from the data, and the data is distinct from the integration with the workflow. So this, I do think, merits a whiteboard. So just briefly, if you consider Facebook, IBM, Salesforce, Google, all these folks, what are they doing? Every other week you hear that they're open sourcing something. So why would they do that? So you have your algorithms, your data, and what I'll call the workflow integration. So let's take an example. I always pick on IBM. I do love those guys, but I always pick on them. Let's take IBM Watson. Right? This is arguably, if you believe Super Bowl commercials from H&R Block, the world's most powerful AI system in the world. And that redundancy was on purpose. What?
Don't they also use the power architecture?
They do actually. So hardware is awesome. Yeah. So that's actually, I'm a huge fan of the power architecture. But let's get back to that in a second. So Watson is an AI system, and it is meant to basically solve the world's ills. It's meant to help with decision making in healthcare. It can do your taxes. It can detect fraud or security break-ins. It's this powerful artificial intelligence. You would think with a system that sophisticated, you would want to lock down all the proprietary information about that. But in reality, it's actually fairly open source. The techniques are there. It's, OK, this is this type of net, these types of filters. This is exactly how we're doing this system. Same is true with like ImageNet, all of the Google stuff, speech-to-text translation, just everything you can think of that's out there that's cool. Even, to some extent, self-driving car code, it's out there. So the algorithms are almost a commodity. It's like a neural net is a neural net. And yes, there's nuance. And yes, at Delta Brain, we do tweak them a bit. But the idea of like my tweak is super proprietary and I hide it, actually, we try to go out of our way to share what we do because that attracts talent. And that's what Facebook and Google and all these other folks do, is they realize the money isn't in the fact that you're sitting on an algorithm. The money is actually in the fact that IBM has more data than almost anyone in the world, and Amazon has more than that. And Walmart has more than that, and the IRS has not that much. Right? So actually, Walmart, 10 years ago, had more data on people than the IRS did. And that hasn't changed. And Amazon now has more data than you can imagine. So if I want to rip off Amazon, I can make an AWS. I can write a bunch of scripts around cloud management, slap a pretty interface on front of it. I'm being a little glib. It's actually quite hard to do that, but we could. Because the concepts around Docker, another open source technology, containerization, deployment, management of swarms of services, all this stuff, you can go get a $10 book and learn it. What you can't do is go build a data center that's 15 football fields wide, right? That's where the power is. And that, to your point, is actually another important piece, which is the hardware. But what's interesting about that point, and the reason why I didn't write it down, is because I can go to IBM or Amazon or NVIDIA, and I could say, hey, do you mind if I pay you like 30 cents a month and I can borrow a whole bunch of your hardware? Sure. So actually, we live in an interesting time where I'm older than I look a lot older. And when I was growing up, I didn't have punch cards. But what I did was we had mainframes and basically self-standing server racks. And when I was 18 years old, I had a job at the college building that rack. And it came in pieces, and I put the blades in, and I did the firewall switch. It's like, nobody does that. They're like, OK, Grandpa, it's all on basically on-demand hardware. If I want the world's most powerful Titan GPU, I just fire up an IBM Power 9 instance on the new test cluster, and I can use one. That's great. So that's fantastic. So if you want to be, and I'm way off topic of your question, but if you want to control the value and the proprietary, all this, forget your hardware, because anyone has access to supercomputing. Forget the algorithms, because just go on archive and read the latest papers from anybody, DeepMind, whoever. The data is where a lot of people concentrate, because they say data is the new oil, right? This is from, God, this is one of those cheesy things that gets thrown around for about a decade now. It's the new oil. We have all the patient medical records. We're going to take your entire genome, and then I'm going to analyze it. I'm going to tell you what day and hour of the day you're going to die. That's very not fun. It's also wrong. It's stupid, because first of all, everyone big has data. So the idea that I'm a tiny startup, I'm going to get a bunch of patient data. It's like, OK, well, go to the Mayo Clinic. They already beat you. So what do you do differently than the Mayo Clinic? What do you do differently than these gigantic organizations, whether they're healthcare systems or even like Google's Verily project, where they're literally just going around vacuuming up people's personal medical information? Thankfully, mostly in Great Britain. You actually focus on this. This is where I think going forward the real value is that you have these people sitting on these barrels of oil, but they can't refine it into anything. If you found out tomorrow your house was on top of an oil well, you'd probably be pretty happy. The first thing you do is call all your friends and brag about it. The second thing is probably you clean your shoes off because you have oil all over them. But the third thing you do is go, oh, what am I going to do with all this gunk seeping out of the ground? You have to actually turn it into useful things like kerosene or gasoline or candle wax or whatever. So this is where the rubber meets the road. This is where you actually use the algorithms running on the hardware. You can borrow the data. We do that all the time. I go, you guys, you have the data. You can keep the data. And that's another thing. It's like a lot of startup companies are trying to sign agreements with hospitals. Like, we own your data. We don't care. It's their data. We don't need to keep it. It's fine. Every time our system sniffs anything, it gets smarter. It doesn't need to keep it. The weights keep that knowledge. What we do is we go, look, you've had data for, I don't know, 50 years. How long has your health system been around? But what you're not doing is using it effectively. Can you tell me what's going to happen next week in any extent? Can you say, this happened 4 weeks ago, this happened 2 weeks ago, what's going to happen next week? They'll go, probably the average of these. This is no good. This is the level, and I want to be nice, and I want to say that they're trying. But the problem is when people wake up and they're on top of an oil well, everyone thinks they're a data scientist, and they're just not. And that's where I feel the real opportunity in machine learning, artificial intelligence, and general just software engineering is actually using your gift, which really, the gift of creativity combined with the knowledge of process is very powerful. Using that gift to help those people solve actual problems that they care about. The second you can tie it to that, you're golden, right? The reason ice cream trucks are still around is because people on a hot day want an ice cream cone. Software engineering is not about making nifty software. It's about solving people's problems. It's about fundamentally meeting a need that is out there. And as software engineers, either professionally, recreationally, or part-time, it is your job to work collaboratively in a group to solve problems for the people that need your help. If you do that, you will be successful.
We'll open it up for questions now, and I hope we get a chance to hear even more about Delta Brain. I just wanted to compliment you on your topical nature. This week we learned about testing.
Oh, really?
We're also studying a little bit about machine learning this week, and next week we're starting our 2-week final projects where students are moving from working individually into working in teams.
Wow.
So this is all very topical for our summer app space class. So we'll open it up for questions, and one question that I wanted to start out with, and then I'll get to you, Nayeli, was could you maybe for 3 or 4 minutes so that we have time to also take questions, talk about one concrete challenge that you've been solving at Delta Brain?
That's a good question.
Oh, sorry, you have a microphone.
Well, first of all, thank you for having me here. This is such a pleasure to be able to talk about things I enjoy. It's a lot more fun than talking about stuff I don't care about. One concrete challenge we had to solve at Delta Brain. Okay, actually, this is kind of fun. So this is one that we hit last week, actually. So we're using, and I won't go into super weedy details, but random forest, blah, 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 mumble, mumble. Okay, just flip to the back of any machine learning book. We're using that, ensemble machine learning methods. And we're producing predictions of the future based on what we're seeing in terms of feature vectors. I'm like, okay, this is great. This works really nice. And oh, look, our crossval, it's all pretty. And this is the stuff that's like the bread and butter of machine learning. And I look at it, and I'm a physicist. My background, I came to Caltech back in the day, and I graduated in 2001 with a physics degree. Then I went off and got a PhD in physics and an MBA. And then I went off and kind of did some scientific computing for the Department of Energy. Sold my soul for a short period of time and worked in finance as a quant, and then redeemed myself by going to SpaceX and being able to work with amazing people. And now I'm kind of on my own with my team trying to actually make it all mean something by building something in healthcare. So it's been an interesting journey, but maybe that's a story for another day. But I'm a physicist, and basically my DNA is I need error bars. If it doesn't have an error bar, I don't believe it. If I say, oh, the weather tomorrow is going to be 95. Terrible. Terrible. You can't, I don't believe that. So no, it's probably going to be, I'm like, 99% sure. Actually, let's be careful. I'm like 80% sure because the weather people, although it is California, so let's make it 85. So it's going to be between 93 and 97 degrees Fahrenheit. That's a much more meaningful statement, because now it's like, okay, you think you know the future, you don't, but you're trying, and you're using data from the past and patterns you're extracting, and you're going to kick the ball out one day, and I predict 95 degrees. But you know what? My model is terrible. It's like really bad. So actually, I think it's anywhere from 85 to 120. That's terrible. So I just told you not just what I think, but how smart my model is. That's an important piece of information, right? Because you talk to people all the time, and you're like, I think it's going to rain tomorrow. It's like, oh, wow, do you have like a thing in your knee? It's like, nope, just stupid. Just think it's going to rain. It's like, I don't listen to that. But I do listen to people who's like, oh, what's your job? I'm like, actually, I'm a meteorologist. Oh, you think it's going to rain tomorrow? Why do you think that? Well, we have actually Doppler, radar all over the, the area, and we're actually noticing a pressure front coming in. So actually, Adam, your machine learning is kind of cute, but actually, we think it's going to be 95 or 95.2 or 94.8, and that's going to be at 2 p.m. tomorrow Pacific time at your house. Someone tells me that, I listen. That's very important information. Without all of this, I lack something very critical for making a decision, and that's context. Context is everything. When you're trying to build a machine learning system, an artificial intelligence agent, whenever you're using any of this really fun, fancy stuff, what you are doing is you are influencing someone's decision. Should we operate on this patient? Should we launch the rocket tomorrow? Is this a cat? These are decisions that are critical that you have to make. Knowing the uncertainty around that is everything. So my long-winded answer to an extremely short and well-defined question is some of these ensemble methods are terrible at producing error bars. So I kind of vowed to the team, I'm like, listen, we're not going to sit in a room with a bunch of chalkboards and invent, a bunch of machine learning algorithms. They're there. What we're going to do is we're going to take them and we're going to put them in production and we're going to help people. We're going to focus on harnessing the best innovations and getting them out there. And now, unfortunately, we find ourselves in a room with whiteboards covered in equations trying to get the darn error bars to come out correct. And so last little thing on that, the way you do that is you start with a... Nope. What aspect of the process? How do I know I'm done? A unit test. So I said, Dougie boy, it's my guy, it's our data scientist. That's your unit test. This is y equals x plus some random junk. And I'm going to fit a straight line through that. And I can do that with my eyeballs or an Excel worksheet. And I can program up the exact answer to when I predict over here, what I think that error bar should be. I know what the answer is. Now build a system that uses an ensemble learner that produces an error bar that matches that within some tolerance. And then you're done. And that's it. And now he's off doing it. I don't have to sit there and micromanage him. I don't have to be paranoid. What we're going to do, obviously, is review all the equations. But the point is, we know where we're trying to get. Because the idea of produce an error bar is too vague. It's really, give me the right answer for a problem I know the answer to so that I trust the system in a problem where I don't know the answer. So I'll zip it and take another question.
Nayeli, did you have a question?
So you talked about how you were the leader of the space science project.
Yes.
How did you direct the people in your group to go work the way you want to, especially coming from a background where they usually work by themselves? Like, working with other people, I've noticed that it's really hard to work together and give the same ideas, even though it's it's totally the opposite. And how do you go about that?
That's great. So that's a great question. It's one that has a long answer, but I'll give the short answer in respect for the time. In a nutshell, so your question, which just to repeat it, is when you have a team of people who are all highly driven, kind of creative individuals, how do you actually make all the cats go in the same direction? How do you lead that team? And in a nutshell, that is the paradox of leadership. There are two types of leadership. There's authority and there's actual leadership, right? And it's kind of like the difference between a manager and a leader, right? You can have someone who manages a team, but they're not really leading people. And you can have someone who's the most junior person on the team, and you see this in movies all the time, right? Where it's like, oh, the head person freaks out or whatever, and then the junior guy's like, all right, we're going to go over there, we're going to take that castle, we're going to kick the door in, and we're going to be heroes. And everyone's like, all right, great. So that's leadership. And the difference is the use of authority. So you can come in, and I could say, all right, I want error bars on this, or you're fired. And how creative do you think your people are going to be? How hard are they going to work to do that? They're going to do the minimum possible thing because they don't think you care about them. So as a leader, I literally I changed the printer toner. Like when someone has, and this actually happened at SpaceX, someone's computer was too slow. I actually went and bought memory and then came and installed it in their computer when they were gone. Like as a leader, you have to serve your team. And the way you get them to do what you need them to do, because ultimately you can have the greatest team in the world and everyone loves each other and you're helping them out and you're all friends. If you don't accomplish your goal, you failed as a team, no matter how functional and happy everybody is. So you still have to get the ball over that finish line, mix the metaphor. So the way you do that is you start by leading by example. You don't tell people, okay, I need you to work all night, bye, right? You sit there and you work hard with them. And you show them that I will write a unit test. I will do this process with you. And then you show them why. And that's really the thing, is as a grown-up person, when someone asks you to do something, your natural instinct is to ask why. And that's a good question, because you should choose, and again, it goes back to decisions, choose to do the right thing. So why should I do a unit test? Okay, well, here's why. When you don't, and that's usually how I train new people on the team, is they kind of ignore me for a while, and then something hideously breaks, and it's like, well, how much code have you written? Oh, I wrote like 10,000 lines. Okay, where are the unit tests? Well, I was going to do those after because I know you said to, but I didn't have time, and I know you wanted the deadline, so I just wrote the code, and it's here, but it doesn't work. I'm like, go ahead and debug that. And then they do that. And then you go back, and they have unit tests, and you say, okay, now debug something later. And they see by example. It takes time. And leadership, as opposed to authority, is about trust. If people don't trust you, you're never going to be able to lead them, no matter how smart you are. I've had people on my team who are way smarter than I am. And they've followed my lead, not because I'm the boss and I come in with a tie and I tell them what to do and look at me. It's literally because we sit down and have a discussion as a team around our goals. And it's always about how do we reach our goal, not what do I want them to do. Because the best kind of person on your team is the kind of person who will actually say, Adam, I know you want those error bars, and I know you gave me this unit test, but all those dots are the same distance from the line. And we might mess up if they actually change distances. So let me give you a function that's like a sine wave, and then we can do that. That discussion actually happened because that person trusted me enough to disagree with what I was asking for because he and I understood the same goal. And those types of discussions are what make a team of 8 able to accomplish stuff that teams of 50 can't.
Thanks so much, Adam. I think we just have time for one more question. Could we take one more question? And then we'll take a short break to use the bathroom before the next speaker, so you'll have the chance to maybe talk with Adam over a cup of coffee as well.
Coffee.
You know how you founded Delta Brain? Why did you feel that you had to go into the healthcare field?
Okay, that's a good question, too. And by the way, I don't usually say that's a good question. It's just you guys actually have good questions. Healthcare is one of those things where if you boil down the theme in what I've talked about, I've talked a lot about collaboration and process. But if you boil down what I've been doing with my life when it comes to SpaceX, that simulation, when it comes to healthcare, when it comes to even on Wall Street making those decisions, it's coming down to decision making. I believe software and data and the mathematics around that data and understanding of patterns is transformative for decision making. It's really transformative. And so the reason I went into healthcare is because that is the place where the decision matters. You can't be overcautious because overcautious may be I cut your leg off, right? So being overcautious is actually just as bad as being sloppy. So you actually have to be right. And it's very rare that you have to be right. If you look at a bridge and you go, oh, I think that bridge might fall down. All right, let's add more concrete, let's add more steel. No problem, usually. Rocket, you can't really do that, right? Because let's add another engine. Oh, it's too heavy. Healthcare, you really can't do that. The other dimension there is the idea that healthcare has been pushed in the direction of digitizing all their data for 20 years. And they've been forced to do it in the last 10. So now they actually have all this data under their house, and they can't refine it into insights. So you always have to look at, and maybe actually I won't say you always have to because that's advice. I'll say for myself, I wanted to look at where my skill set and interests fit into the arc of history, right? If I wanted to make and I was going to use flying cars as an example, but they're actually coming out with those. But if I wanted to make a teleporter, I'm probably a little bit early for that, right? If I wanted to work on steam engines, I'm probably late for that. So where in the arc of history are we today, and where can computing, data science, artificial intelligence, and just general coolness get us? And I feel that that intersection is healthcare. And I feel like when I look back a decade from now on these, what I think are my most productive years right now, I want to be able to say, like, man, we helped with the rocket, and then we actually helped a whole bunch of people. And we work with a children's hospital now. So the idea of combining what I do that I love to do with a mission is why I started Delta Brain. And it's a lot of fun.
Wow, what a powerful note to end on. Let's thank Dr. Lichtl. Thank you. It's an honor to have you back here at Caltech. And we'll take just a short break. There's a bathroom right around the corner to the left. You can have a little drink of water. And then we'll come back and I'll introduce Dr. Ramirez.